Hey there. So today we are going to talk about a very interesting topic, that is Bohr's atomic model. Now before we get on to Bohr's atomic model, we have to cover a few basics, that is about the emission spectra, because it was very uh, important for it is very important to understand his model. So the basic characteristics of wave. Now we know that wave can be described by two important characteristics. One is that of a wavelength and the other is of a frequency. Now, what is a wavelength? It is the distance between two crests or two troughs. So this is the two crest number one, crest number two, and the distance between those can be called as a wavelength. Now, how many times you can have these crests in a particular interval of time? Let's say a second. That counts for frequency. So if you talk about visible light, so visible light has all wavelengths. So generally when we say talk about visible light, that's 400 to 700 uh, nanometers. But obviously there's light beyond, there are waves beyond 700 and less than 400 as well. 700 is the red, and 400 is the blue, right? So we have infrared and ultraviolet, means something that's lower than blue. But how do we find out? So when we push the white light through a prism, now I hope you know about prism, right? So when you put the white light through a prism, this expands to give you the seven colors. Now this is how you came to know about it. But obviously the seven colors is 400 to 700 that you could see. There are others that you cannot see, right? So, and how are these quantities related? That is the wavelength and the velocity of the light. So lambda is equal to c by v. Now lambda talks about the wavelength and c is the speed of light, that is 3 into 10 to the power 8 meter per second, and v stands for the speed of the wave that we are talking about. So that's the relation between lambda, c and v. Now, why are we talking about all of this? So that will be understood once we talk about what happens when we push the light that we know of into a gas chamber which is under very high pressure. So we put down electrodes here and we find out what changes, look for changes that happen to the light. Now, how do you spot the changes? You put the light under a prism. So you first pass the light, from the prism and let it again fall on a film. So you capture the colors or the reflection once again. Now what you see is, before it had passed through the gas chamber, it was a continuous spectrum. That means there's nothing missing, right? There's not nothing missing. So if I talk in terms of colors, so you see a continuum from V to R: violet, indigo, blue, green, yellow, orange, red. It's just an analogy to understand this. So you see a continuum, right? You see a continuum from V to R. But once you pass it through the gas and then after the prism, you see gaps, right? You see gaps. Some of the wavelengths are not there. So your mind questions what happened to those wavelengths, right? Why only those wavelengths are missing? When we pass the light, only a few spectrums come out and we say that this is the emission spectra, that is the light that is emitted by the gas, but exactly it's the opposite. And whatever is held back, we call that as absorption spectra, right? So something that the gas absorbed. So why are there gaps? Because the gas absorbed it. Why did it absorb? We do not have a clue. And remaining part is emitted out. Now two great scientists, Balmer and Rydberg tried to find a mathematical relationship. Is or is it possible to come up with a mathematical relation between these wavelengths? So what he found was he found the relation between about the wavelengths of hydrogen. When the light was passed through hydrogen, he said that the wavelength would be can be expressed as a relationship of R n1 and n2, where n1 and n2 are integers and R stands for this number. Now, it's very important for us to understand that he did not understand the significance. What is the significance of n1, n2? Why we are getting uh, 1 by lambda? He did not understand that. Bohr was a Danish scientist who came up with an explanation. So what he said was, well, there's one way to understand all of this. If the atom had fixed orbits, if the atoms had fixed orbits, fixed circular orbits around itself, and the electrons revolve in those fixed orbits, because of the charged nature, we can expect that these orbits must have fixed energy, right? Each of these orbits must have fixed energy in each of them. So when you want to jump out or when you want to jump in, this would involve an energy transition. So let's say you want to jump out, so that means you need energy. So you want to jump out, that requires energy. You want to jump in, so when we provide the energy, that can push the electron from the lower orbit to the higher orbit. But since it's not very stable, it needs to come back. So when it does come back, it will release that energy back, right? And this is what we find in the spectrum. He even gave a formula for it to find out the radius of where the electron can be. So that is given by r, that is the radius, equals n square a naught. He gave the value of a naught, that's 5.292 into 10 to the power 11 meters, and n has to be a positive integer. Now, to find out what is the energy of the electron that is in the orbit, he gave a very separate equation, which is, okay, minus 1 by n square, bracket h square by 8 pi square ma naught square. Now, because you know that the quantity like h, that is a Planck's constant, then pi, it's a constant again, 3.14, m is the mass of electron, as we already know about, and the a naught, that is the Bohr's radius, that is already given here. Hence, if you put in all the values, you consume all the values, you get 2.180 into 10 to the power minus 18 upon n square. So what he basically tried to show is that the farther away you are from the nucleus, the more energy is required, right? So to be away from nucleus, you need more energy. So this was his way of talking about the electrons. He said that electrons revolve around in the orbits, and each orbit has got a fixed energy, and the gaps are because the electrons absorb the energy. So whenever there is a jumping out or jumping in of electrons, the corresponding energy, this E, can be emitted as, energy is hc by lambda. So this wavelength that was in the emission spectra, he could explain it by relating to this. So this is what he wanted to explain. But I want you to understand that this model did not hold. Why? In further videos, you will talk about topics like Heisenberg's uncertainty. So actually, he felt that the Niels Bohr, he felt that the energy is quantized. Now, in fact, we do have quantum numbers that help us to describe the state of the electron, but it certainly doesn't revolve around in orbits, right? So you can't have the position and the momentum of the electron at the same time. So Heisenberg uh, uncertainty principle kind of outthrew Bohr's idea. But nevertheless, Niels Bohr's concept was a great deal when it came to atomic models because it improved the understanding by a lot. I hope this helps.
Physics doesn't have to be hard. Subscribe to our channel and learn with the geeks.